Okay, so in today's lecture, we will talk about a very important topic, which is network growth model. Okay. Now, what is network growth model? Why network growth model is important to study, right? And why we should care about doing research on network growth model? We'll discuss here. We'll also discuss we'll also discuss some of the typical network growth models that people generally use to mimic real world network structure. Okay. So we have already discussed in the previous lectures that over time we have seen exponential growth of social network usage, be it Facebook or YouTube or WhatsApp or any platform, right? And this graph clearly depicts how the growth has happened in last, say, 5 to 8 years, right? Not only that, if you look at the number of people accessing the social network every day, for example, in 2015, Twitter has around 288 million active users and 60 billion followers, right? And this has grown a lot, in fact, after 2015, right? So now, such huge network, right? When you think of any application, say the application is link prediction or the application is node classification, right? So with such a huge network, you may not be able to run your own model, right? Because your model may take a month, for example, right, to run and to produce something. So what's the remedy? So a remedy is that you try to create some synthetic networks, okay, which look like a real network. For example, say you have a model and your model knows how a real world network grows, okay, how nodes get attached, how nodes get deleted, how edges get attached, edges get deleted, and so on. Let's assume that there is an oracle and the oracle knows how these real world networks evolve over time, okay. What's the growth pattern, what's the growth dynamics. Then you use that model to generate synthetic networks, and then the size of the network will be in your hand because you can easily control the size, and you can generate networks of different sizes. For example, say you just want to check the efficacy of your downstream task, right? You generate a small network and you just check the accuracy, right? Then you keep on increasing the size of the synthetic network, and then you keep on testing. And to test the scalability, once your prototype is ready, your POC is done, right? Proof of concept is done. Then you take the real network, the gigantic network that you have, and then you test it on that. Okay. This is one reason. Another reason is that in most cases, real world networks are difficult to scrape, right? So let's think of Twitter. Now, Twitter is a platform which you can still scrape, whereas platforms like Facebook, right, WhatsApp, you can't scrape. This is not allowed. Where Twitter you can scrape, but that too, you get 1% sample of the entire population, right? So this 1% or 2% samples of the entire network is just meaningless. Okay, so you may not be able to get hold of the entire network structure if you do not belong to that company. If you're part of the company, you can still get the access of the network. But if you are an academician like us, right, we don't have access to the entire network, right? And there are many privacy issues. For example, say if my account is locked, right, so your scraper would not be able to scrape my details. So for example, my followers or my friends, right? So there are privacy issues. There are shortcomings of the crawler to scrape entire data. And of course, there's a problem of accessing large data. For that, what we try to do, we try to generate synthetic networks, right? Synthetic networks means networks which look like real world networks, which try to preserve most of the real world properties, right? And then you can use your algorithm to test on this synthetic networks, right? And then once you are satisfied with the result, you then scale up, you move to the real world network, and then you test it. Okay, so this is called network, synthetic network. Okay, so synthetic network, as it is written here, generated using some theoretical network model. We will discuss many such theoretical models by which you can generate networks. And often it often possesses a strong underlying mathematical foundation, often can simulate important real world characteristics, help getting insights of the real world network, allow experimentation through simulation when real networks are unavailable, can establish network insights on concrete theoretical foundations. Okay, so this is the task, right? So now, what are the typical properties that you would like to preserve in a synthetic network? So you would like to preserve these three properties because these three properties are kind of universal across all sorts of real world networks. Okay, the first property is that high average local clustering coefficient. Local clustering coefficient we have already discussed. The number of actual edges among the neighbors divided by the possible number of edges among the neighbors, right? So in most real world networks, we have seen that the local clustering coefficient is pretty high. Okay, so this should be preserved in your synthetic network. It should also follow the small world property. So this thing I will discuss, what is small world property, and the synthetic network should also follow the scale free property. This we have discussed briefly, we'll again discuss today. So we'll try to preserve these three properties in the synthetic network. Okay, if we preserve these properties in the synthetic network, then you can claim that your synthetic network looks like a real world network, right? So whatever hypothesis you propose, and if those hypotheses are valid on the synthetic networks, that means that those hypotheses would also be valid for the real world network. Okay, so average clustering coefficient, average local clustering coefficient, we know how to compute, but if you look at the, if you look at the real world network, for example, a Facebook social network, social network for a user of 100 friends, that means a user has degree 100. Okay, so user has 100 degree, the clustering coefficient is still 14%. Right? So this is quite unexpected because, as you understand, as the degree grows, number of friends grows, it is less likely that friends would be connected. Right? So say, for example, I have 5 friends versus you have 1,000 friends. Right? So it is highly likely that my 5 friends would be more connected than your 1,000 friends. Because ultimately, when you calculate the local clustering coefficient, the denominator is very important. And the denominator is NC2, right? So DC2, D means the degree, right? So if this grows, then it is very unlikely that the numerator will also grow with the same pace, right? So, our intuition says that high nodes with high degree generally have less clustering coefficient, which is also true, but still a node with 100 friends, if the clustering coefficient is still 14%, which is actually great, which is quite high. Okay, so a Facebook network with 150 million nodes, the average clustering coefficient turned out to be very high, around 0.8, 0.18, 0.19, 0.20, 20%. Okay, and this is something that you need to preserve in your synthetic network. Whatever mechanism you use to generate synthetic network, your synthetic network should have high local clustering coefficient. Okay, small world property. Now this is very important. The small world property is a very interesting property that was discovered around 1970s. And so basically, the idea is that our world is very small. That means if you randomly pick 2 nodes from the network, from a large network, right? The distance, the shortest path distance between these 2 nodes should be very small. Okay, and in fact, it turned out in the first experiment, it turned out that the shortest path distance between 2 nodes, 2 randomly chosen nodes, is 6. Okay, I will tell you the experiment that was conducted. Now, this is called 6 degrees of separation. This famous term 6 degrees of separation was basically coined after this particular experiment. Okay, so it means that the distance between you and Barack Obama, for example, right, is 6, right? So which looks like very non-intuitive, because so it is basically saying that there are only 5 nodes or 5 users in between you and Barack Obama, right? But I mean, if you think of it naturally, right? So the intuition may not support that claim, right? So let's look at the small world experiment that was conducted by Stanley Milgram, right? So so Stanley Milgram, so he's a famous American social psychologist, right? He's also he is very known for a lot of crazy experiments that he had done, right? So he conducted this experiment in 1967. Okay. Now, what was this experiment? So he chose 2 different cities in US, right? One is this Nebraska, Omaha, and Kansas here, right? So this is the starting point of the experiment, and this is the ending point of the experiment, which is Boston. Okay, so this is the starting point and this is the ending point. As you see, these 2 basically places are far from each other, so therefore it helped doing this experiment. Okay, so what was the experiment? So around 296 letters, okay, around 296 letters were given to random individuals in Omaha. Okay, and each letter, and what was the task? The task was, so he told this the senders of these 296 letters that that there is an unknown destination address, right, of Boston. So these 296 senders need to send these letters to that unknown destination. Okay, so each letter had the following details: the purpose of the study, right, and some basic information about the destination. Okay, now each sender was asked whether whether the sender knows the destination, right? If the sender directly knows the destination, then he or she can directly send the letter, right? But if the sender doesn't know the destination, then the sender was asked to send the letter to her friend or relative who the sender believed that knew the destination. Okay, say I want to send something to Boston. I am located in Omaha, right? So say I do not know the destination address, right? But I know, okay, the person X may know this address. So what I will do, I will pass the letter to person X with the hope that the person X should send the letter directly to the address. Right? Remember, this is shortest path. So you always try to minimize the overall hops, total number of hops needed to reach the destination. Okay. So out of 296 letters, only 64 letters reached the target contact. Okay, which may not be statistically significant, but at that time, since this was a social science type experiment, then it was accepted. Okay, and it turned out that the minimum hop needed was 1, so direct connection. Some of the people knew the destination and they therefore directly sent the letters. So minimum distance was 1. And the maximum distance was 11, maximum hop distance, okay, with a median of 5.2. Right now, 5.2 is near to 6. Now, why not it is near to 5? I don't know, but it is near to 6. So therefore, the term 6 degree of separation was coined. Okay, and so then Milgram said that any you take, and then Milgram tried to generalize this hypothesis that let's take, if you take any 2 individuals in the world, the distance should not be more than 6 based on this experiment. And later on you easily understand, right? And a lot of debated lot of debate started that, okay, this is not a valid one, or the sample size is less, and so on. So the same types of experiments again was conducted in 2007, right, through online world, and this time through Microsoft Messenger, right, by Leskovic and his team. And it turned out that the distance is 6.6, which is very similar to 6, the one that Milgram mentioned. Few years later, in 2011, Facebook did this experiment, right, again in the online setting, and it turned out that the average the average path length is 4.74, even lesser than 6, right? Facebook repeated the same experiment later, and then at that time it turned out to be 3.74. So then, Facebook coined the term called 4th degree of separation. They said that no, the world is getting closer and closer. Okay, so in Facebook there's an app through which you can measure the you can measure your degree of separation. In fact, I measured my degree of separation, which turned out to be around 3.48. You can also do the same experiment. You can check your degree of separation on Facebook. Okay. Now this is called small world property. So the small world property says the average path length between any pairs of nodes in the network should be very less, right? In fact, it turned out to be the average path length. The average path length is log of n, where n is the number of nodes, or log of n, right? So this property should be preserved in your synthetic network. High clustering coefficient, less average path length. Okay. Third property, scale-free property, I have already discussed in the previous lectures. So basically, the scale-free property is applied to the degree distribution, right? So we have seen that the degree distribution in real-world graph follows a power law kind of distribution, which basically looks like this: y is x to the power minus alpha, right? And so here b, right? And this is called the coefficient. It basically ranges between 3 to 4 or 2 to 4, right? And this is called scale free because the functional form remains proportional to the original function if we scale the variable, right? For example, if you scale x by cx, the resultant function would be proportional to the to y. Okay, so it basically scales up or scale down, but the functional form will remain same. Okay, so we have seen graphs like this, where the x-axis is the degree and y-axis is the so x-axis is the degree k and y-axis is pk. Pk is the p sub k is the probability of a particular node with degree k, right? And we have seen this kind of skewed power law distribution, which basically says that there are a lot of users with less degree, right, where there is a very small number of users with very high degree. Okay, there are a lot of users with less degree and small number of users with high degree, right? Now this is also similar to something called the Pareto Principle, right? In economics, this Pareto Principle is very famous, right? Which basically says, which is also called 80-20 rule. I'm pretty sure you guys have heard about this rule, which basically says that 80% of 20% of users have 80% of wealth. 20% of individuals have 80% of wealth, and 80% of individuals have 20% of wealth, which is very obvious, right? If you look at our society these days, right? So all these big giants, they already occupied lots of properties, lots of wealth, right? And this is also called the law of vital few, is also called the principle of factors sparsity, right? Pareto principle, 80-20 rule. so on and so forth, right? And therefore, this power law is also called Pareto distribution. And if somebody says, what is Pareto distribution, you should be able to say that, okay, this is basically power, right? So as I mentioned, the real world property for the real world graph, the degree distribution follows power law. It means that if you plot it in log scale, the degree distribution, you see a degree distribution follows a line, which is basically a property of a scale-free network, right? So if you are asked that that what is a scale-free network, you should say that the scale-free network is something whose degree distribution follows power law, Pareto distribution, right? Now, these three properties should be preserved in a synthetic network: high local clustering coefficient, small diameter or whatever, the average path length, and smaller property, scale-free network. Okay. So now let's start with the model. Now this is the first synthetic network generation model, which was proposed way back 1960s. Okay. And this model is called random graph model or random network model. And this was proposed by Ardos and Rennie. Ardos and Rennie, they are very famous mathematicians, and they proposed this model. And this is a very simple idea. The idea behind this model is that, say you are given n number of nodes, right? So let's start connecting nodes randomly. Okay. So there are two different models of random network proposed in the literature. One is proposed by Ardos Rennie, where a random network is denoted by G n comma k, right? What is n, what is k? N is the number of nodes and k is the number of edges. Okay, so it basically says that let's take n nodes, let's take k different pairs of nodes randomly and connect them. Okay, there is no principle. This is called Ardos-Rennie random graph. So this is one way, and the second way of representing the random graph is G n comma p, right? Where n is the number of nodes, and what is p? P is the probability of two nodes being connected. Okay, now how this network is formed? There are n nodes. You choose a pair of nodes, right? Again, randomly, you toss a coin. With probability p, you connect. With probability 1 minus p, you do not connect. Very simple. Okay, with probability p, you connect. With probability 1 minus p, you do not connect. Now, in the second model, in the second version of the model, there is no guarantee on the number of edges that will be produced, because this all this all depends on the coin toss. Whereas in the first case, the number of edges is fixed, which is k, right? But in the first case, there is no explicit probability that we take into account. Okay, so generally we consider the second model, right, which is proposed by Gilbert around the same time, right, G n comma p, as the de facto random graph model. Okay, now this is an example of a random graph where you have 16 nodes and the probability is 1 by 7. If you have this probability, you can look at this kind of graph. Okay, now it is very intuitive that this kind of models, this kind of graphs would not be able to preserve the three properties that I mentioned, right? Because this is the because real world networks do not form randomly. Okay, but still we need to study this model, because then you will understand that what are the drawbacks of this model and how the other models came into picture to solve some of the drawbacks. Okay, so now let's study. Now, so what are the things that we need to study? We need to study the degree distribution, because degree distribution would ultimately give you the idea of whether it follows a scale-free distribution or not. We'll need to study the average path length. That would give you the idea of whether this is a small world graph or not. We need to study the local clustering coefficient. Okay, these three properties we study here. Okay, so let's look at it. Okay, so the graph is G n comma P, where n is the number of nodes we know and P is the probability that two nodes are connected. Okay, so if I ask you that how do we define the probability that there are k number of edges in the graph, because we do not know. So we remember, as I mentioned, in this model we know the number of edges is k, but in this model we do not know the number of edges, right? So we need to determine the number of edges. So let's assume that pk, okay, p capital K is the probability of k number of edges in G, right? So how do we determine this one? So what are the possible number of pairs there in the graph? It is NC2, right? And remember, each edge, the success of forming each edge is P, and failure of forming an edge is 1 minus P. Now this is a binomial distribution, right? So you're basically saying that out of this many experiments, right? Out of this many experiments, what's the chance that k experiments are successful, right? So NC2, right? P to the power, NCK, P to the power k, 1 minus P to the power NC2 minus k, right? So you have total sample size NC2. Out of that, you choose k. Now k is your success, right? And your success probability is P. So it is P power k. And failure probability is 1 minus P, which is 1 minus P. And what's the failure, the failure number, right? Sample NC2 minus k, right? So this is the probability that k number of edges are present in this random graph. Okay. So if this is so, then look at this equation. Okay. If this is so, since this is a binomial distribution, right? What is the average or what is the mean value of this variable, random variable k? It's capital K. Okay. What is the mean of this binomial distribution? N into P, right? So what is N? N is the sample size, total sample size, which is this one in our case, which is NC2. So this times P, this is the mean, right? So this is N into N minus 1 by 2 into P, right? Right? So this is the mean number of edges. This is the mean number of edges that can be generated using this random graph model, right? Why we are interested in mean number? Because this is a stochastic process. Every time you toss a coin, so you have one setting, you have in one setting you toss coins multiple times to generate k, right? You may have one value of k. In another setting, you may have another value of k. This is a probability. Therefore, we are always interested in the mean value. So the mean value of the number of edges is this one, n into n minus 1 by 2 times P. Okay. So now if this is the mean number of edges present in the graph, right? So what is the average degree of this graph? Because we are interested in degree distribution, right? So we need to look at the average degree. So what is the average degree? So average degree of a graph is very simple. You basically look at total number of edges divided by number of nodes, and that's the average degree. Okay. So total number of edges. You mean basically the sum of all the degrees, right? Sum of all the 2 into total number of edges. So how do you calculate the average degree? You look at sum of all the degrees by number of nodes, right? By number of nodes. So sum of all the degrees we know that is basically 2 into number of edges. We know this theorem, right? 2 into number of edges, capital K, right? And this is nothing but this one. So 2 into n minus 1 by 2 into p by capital N. So it's n and cancel out, 2 and 2 cancel out. So this is n minus 1 into p. So the average degree of this random graph is n into is n minus 1 into p. Okay, now think about it. Let's stop and just ponder. Okay, so the average degree and mean number of edges in the random graph both are linear to p, isn't it? Both are linear to p. It means as p grows, as p increases, what would be the number of mean number of edges as p increases? So if p equals to 0, if p equals to 0, then this would be 0. If p equals to 1, because p is a probability, ranges from 0 to 1. If p equals to 1, this is n into n minus 1 by 2. That means when p equals to 1, then your graph is a click. All pairs are connected, which is very obvious because whenever you toss a coin, you see that all pairs are connected. So as p goes from 0 to 1, you see that it moves from the mean number of edges moves from 0 to n into n minus 1 by 2. Similarly, the degree, if p equals to 0, then the degree is 0. If p equals to 1, the mean degree is n minus 1, which is again intuitive because I already mentioned that p equals to 1, the graph is a click. Therefore, each node will be connected to n minus 1 other nodes in the graph. Okay. Okay. So now we learned what is the, let me open a slide. Okay. Let me open a board. So we learned that average number of edges is n into n minus 1 by 2 times p, and average degree is p into n minus 1. Okay, for a random graph model G n comma p. Okay, this thing we learned. Now we know the average degree. Now let's look at degree distribution. Okay, degree distribution. So in degree distribution, what is our aim? Our aim is to find a probability pk that a particular node. So what is pk? We have already seen. We have already seen in this notation. Pk is the probability that randomly selected node has degree k, right? So please remember, this is small k and this is capital K. Okay, capital K is a number of edges. Okay, small k is a degree, right? So now how do we define it? How do you measure this quantity? So for a node to have degree k, the node must be adjacent to k other nodes in the graph. So we can select k nodes at random from the remaining n minus 1 nodes. Think about it, right? So for a particular node, there are total n nodes. So if you do not consider this node, so there are n minus 1 nodes, right? So in order to be able to to get k connections for this particular node, what we need to do? We need to choose k connections or k nodes from this n minus 1 nodes. right? So we need to choose from n minus 1 sample, we need to choose k. And we know that the probability of forming an edge is p. So this is p to the power k, and then 1 minus p to the power n minus 1 minus k. Now this is your pk, right? Again, binomial distribution, right? Now we know that now, right? So this is the distribution. Now again, go back to the slide, right? Now it looks like this, right? So this is degree, and this is pk, okay? And in these three different curves, you basically vary n, because this is n minus 1. So this is the formula, okay? So in the solid line here, n is 1000. So if you fix n as 1000, if you vary k from 0 to n minus 1, right? You see this kind of curve. Binomial, you see it is a clearly binomial distribution with n equals to 1000, 2000, and 3000. There are different shapes, right? So now we all know that as n moves to infinity, what happens? A binomial distribution starts moving towards positive distribution at n tends to infinity, right? So we can approximate this binomial distribution one by a positive distribution, which is pk e to the power, right? E to the power mu to the power k by factorial k, right? What is mu? Mu is the mean, right? And mu, how do you compute the mean? I mean, say you have a binomial distribution pk, which is nc2, nck p to the power k 1 minus p to the power n minus k, right? So and when you approximate this, so your mu would be, so this is mean, right? This is bolo. Any idea? Please unmute.
Sir, n into p.
Very good.
For binomial.
So then it would be right. In our case, this is in our case n is basically n minus 1. So n minus 1 into p. Right now, n minus 1 into p is what? N minus 1 into p is d. So this would be, so mu would be average degree. So this is equivalent to p of k, which is e to the power minus d mu to the power, d to the power k by factorial k. Right now, let's look at the notation again. Pk is the degree distribution. It says that the probability that a random node has degree k, it is e to the power minus d. So this d is this is mod d. This is the mean degree, right? Now mean degree to the power k by factorial k. So this is the degree distribution when n tends to infinity. Okay, this is easy, right? It is not that difficult. Now, what we will discuss is very important. We will discuss the evolution of, so what we have seen, what we have learned here, we learned that the degree distribution of a random random growth model is not scale free, not power law, but it is a binomial distribution, a positive distribution, right? Therefore, this property doesn't hold. Okay, now let's look at other properties. So before deriving the other properties, let's look at how this random network evolves. Okay, now what is the question that we are asking here? We are asking here that what is the criteria, right, after which, or what is the criteria, if the criteria satisfies, we see an emergence of a giant component. Now, what is a giant component? I have discussed in the first day. The giant component is basically a connected component, right? A connected graph, which has most of the nodes present. 80 to 90, in fact, more than 90% nodes are present in the giant component. And the other components are disconnected and they can be safely ignored, right? So the question that we are studying here, that, okay, so let's assume that you have nodes, right? N number of nodes, and you keep connecting pairs of nodes, right? You toss a coin and connect. You again toss a coin and connect. What happens with this? Number of edges keeps increasing, and and then the graph gets connected and connected over time, right? So after a certain point, you see that most of the nodes are connected. Remember, I'm not talking about completely connected graph. I'm just talking about connected graph, meaning that if you choose any pairs of nodes in that connected component, you see there's at least a path. Okay. So as we keep increasing the number of edges in the random graph, you see that after a certain point, a giant component emerges, meaning most of the nodes are connected, right? So we just want to understand the point after which this giant component emerges. Okay, and we will study the criteria of the emergence of a giant component. Okay, and what is the theory? The theory says that a giant component, GC, a giant component emerges in a random network when the average degree of the network is greater than equals to 1. This is very non-intuitive. What it is saying, try to understand. It says that you need at least 1 degree 1 for each node to form a giant component. Now you may say that, okay, degree 1 node is very simple. I mean, you can easily get a degree 1 node. But does this really imply that if on an average, if nodes have degree 1, right, it produces a giant component? Now, this is very surprising, right? We will prove that this is the case. Okay. Now, you can also intuitively understand it, right? If you start thinking that, okay, let's assume that you have a network and you have a kind of a chain-like structure, right? Or a chain-like structure or a star-like structure, where most of the nodes have degree 1, and there is one node whose degree is very high. All the other nodes have degree 1. Then also giant component is formed, right? But if you think in a different way, that you may start questioning that, okay, it's very surprising that with only 1 degree is sufficient to form a giant component. Okay, and we'll prove this theorem here. Okay, giant component, again, the idea is that all pairs of nodes are connected. Okay, if V is connected to U is connected to V, right? If U is connected to V, if U is a part of the giant component, V is also a part of the giant component, right? If U and V are connected, if U is a part of giant component, V is also part of the giant component, right? Because except the giant components, if you look at the other components are disconnected from the giant component, right? So whatever nodes connected, with the nodes in the giant component, they are also part of the giant component. This is very important. Okay. Now let's look at the theory. So let's assume that, again, I'm moving slowly. This is little complicated. So if you have query, just feel free to interrupt me. Okay, but please look at this theorem proof. So let's assume that there are two nodes, Vi and Vj. Okay, let's take 2 random pairs. It's a random pair of nodes, right? And let's assume that let's assume that Vi is in GC. Vi is a part of Jan component, right? Okay. So therefore, it must be connected to another node Vj, which is also in GC, right? So now let's assume that Vi, right? So Vj is also part of GC. Okay, we started with the assumption that Vi. Let's assume that Vi is also a part of GC, and Vj is also part of GC, right? So now, if Vi does not belong to giant component GC, so we denote GC by giant component by G sub C. Okay, if Vi does not belong to GC, this particular thing happens in two different ways, right? Remember, right? So this particular thing happens in two different ways. The first way is that it means that Vi and Vj doesn't exist. This edge does not exist. Okay, because if Vj is, I have already mentioned that Vj is a part of Jan component. Now, if Vj is a part of Jan component and Vi is not a part of Jan component, right? That means this edge doesn't exist. If this edge exists, then Vi would also be a part of Jan component. But what are the criteria that Vi does not belong to Jan component? This is one criteria. And the other criteria, so this is kind of and or, right? Both of them are possible, either one of them are possible. So another possibility is that this particular edge, Vi, Vj, this exists, but node Vj does not belong to GC. Little tricky, right? So what I'm saying is that let's assume that Vi is a part of GC. Okay, so it must be connected to another node Vj, which is also part of GC, right? Now, if Vi does not belong to the Jan component, right? So what are the possible cases? So one possible case is that the edge Vi Vj doesn't exist, because if this exists, then by default Vi would be a part of the Jan component, right? So this doesn't exist. Or if this edge exists, that means the other node Vj is not a part of Jan component. Okay, so this scenario is, let's say this is S1 and this is S2. Okay, so we will measure the probability of S1 and S2 separately. Okay, so let's define another quantity P, which is the probability of a random node V belonging to GC. Okay, this is a probability that you choose a random node V and it's a part of GC. What's the probability? This is mod GC by N. What is mod GC? Mod GC is basically NC. Okay, NC is the number of nodes in the Jan component. Okay, so total number of nodes in the Jan component divided by the total number of nodes in the graph. So this is the probability that a particular node belongs to the Jan component. Okay.
Excuse me.
Yes.
I think it should be Vj doesn't belong to GC. You wrote, I think, belongs to GC.
Which one? This one?
Just on the left side. But Vj belonging to GC. Yeah.
The S2 case.
In S2 case.
No, but no. So this probability is different from these situations. This is I'm defining a new probability here.
No, that is correct. In S2, right?
Oh, yeah.
Yeah, this one.
Yeah, sorry. Yes, correct. So, okay. So I'm defining this one. Okay. So this is the probability that a particular node belongs to the Jan component, which is GC by N. Okay. And let's denote another quantity M, which is just 1 minus P, right? Meaning that the node doesn't belong to the Jan component. Okay. So now, what is the probability of scenario 1? Right? Scenario 1 says that this particular edge Vi Vj doesn't exist. What is the probability that the edge doesn't exist? Okay, let us denote this by capital P, okay, otherwise you will get confused. This is capital P. Capital P denotes that a node belongs to a giant component, okay, a random node. So what is the probability that a particular edge exists? P, small p, we have already started with this notation. G, N, comma P. This is the random graph model, right? And P is the probability of forming an edge. So this edge doesn't exist is 1 minus P, right? Probability of this first scenario. Probability of the second scenario. What it says? That the edge exists. So the probability is P, the edge exists, but the particular node doesn't belong to GC. What's the probability the particular node doesn't belong to GC? M. Right? So P times M. Clear? Right? So M is the probability that a random node not in GC. Okay. So what is the total probability that a particular node does not belong to the giant component? This is this plus this, right? So 1 minus P plus P times M. This is the combined probability. Now this so this particular probability is for a particular node, VI, a particular node VI, right? Particular node Vi, keeping Vj fixed. Now for other n-1 nodes, why n-1? Because already we fixed a node Vj. Now for other n-1 nodes, the same things hold. So therefore, when you try to generalize it, this is for one node. For generalizing this thing, the same probability would be 1 minus P plus P times M to the power n-1. Right? Things are independent to the power n-1. What is this? So this is the probability that a particular node does not belong to the giant component. Right? The particular node does not belong to the giant component. Now look at this. This is same as what? This is same as M. This is same as M. Right? This is same as M. So if you take log in both the sides, so ln of M equals to n-1 ln 1 minus P plus Pm. Okay. What is P? P is the probability of forming an edge, right? And we have already seen that P is mod D by n-1. You have seen P is mod D by n-1, right? So P is mod D by n-1. Okay. Now replace here. So n-1 ln 1 minus mod D by n-1 plus this times 1 plus M, 1 minus M, right? I'm taking P common. from both sides and replacing p by d by n minus 1. Right? So now this the whole part is a part of log. So this is same as log of 1 plus x. Right? Now when x tends to 0, right? So we know that when x tends to 0, log of 1 plus x tends to x. Right? If you unfold log series, you will see this. Okay. So when x tends to 0, when this part tends to 0, so we'll get n minus 1 times what? Times minus mod d n minus 1, right? Times 1 minus m. Okay. Now n minus 1 will cancel out. So you have log m equals to minus mod d 1 minus m. Okay. Now this is the equation now. Again, what is m? M is the probability of not being a part of giant component, and d mod d is the average degree. Okay. Now let us denote another quantity, introduce another quantity called h. What is h? H is the fraction of nodes in the giant component GC, right? Which we already denote as GC by n, mod of GC by n. This is the fraction of nodes in the giant component. Okay, mod of GC, mod GC by n. And what is mod GC by n? Mod GC by n, if you go up, right? We have already seen that P equals to mod GC by n, right? Right now, this is same as H, right? This is same as H, right? So mod GC by n, right? If you replace P by H for the time being, right? You will see that H equals to 1 minus m. H equals to 1 minus m. Right? H equals to 1 minus m. So H equals to 1 minus m. So this is mod of T H. Okay. And just a minute, let me do some calculation here, small calculation, which is m equals to e to the power minus mod d 1 minus m, right? So 1 minus, then I'm substituting one. I'm substituting this part from 1 both the sides. 1 minus e to the power minus t 1 minus m, right? So this is h, and this is 1 minus e to the power mod t h. Okay, so I have written everything in terms of degree and in terms of the size of the giant component. This is the size of the, this is the fraction is basically size. First, the size of the giant component and the degree. Okay, now we need to solve this equation. Okay, now this equation doesn't have any, so this is an open form equation. This is not a closed form equation. Why? Because you see that the h is there in both the sides. So it doesn't have any closed form solution. Right? So when this kind of equation is encountered, how do we solve it? Generally, we solve it in the following ways. Okay, we basically solve it empirically, right? So this part, let's assume that this part is y. Okay, so you have two cases. One is h equals to y, and y equals to 1 minus e to the power minus th. Now let's draw a curve, okay, where x-axis is h and y-axis is y. So h equals to y is nothing but this kind of curve, okay, and y equals to this one. How do we plot it? Okay, because here another variable is d, mod d. So we need to fix mod d first, and then we can vary mod d, and we have different graphs, different curves. So if mod D equals to 0, right? This is trivial. Mod D equals to 0 is trivial. Let's assume mod D equals to 0.5. Okay, so you fix 0.5 here, you vary H, and you get a curve of Y. Okay, and you see that the curve would look like this. So this is H, this is Y equals to 1 minus e to the power minus dH, where mod D equals to 0.5. Okay, if you plot, you see the curve looks like this. If mod D equals to 1, the curve looks like this. Right here, mod D equals to 1. Okay. If mod D equals to 1.5, you see the curve would look like this. Mod D equals to 1.5. Okay. Now we are done, because we are interested in this point, right? We are interested in a point where H equals to Y and Y equals to this intersects, because these two things are same. So we need a value where H equals to where both these equations satisfy. So we need this point, right? Right now there are two such points. One is this one, other is this one. Now this one is trivial. This is 0, so we ignored it. And the next non-trivial point is this one. So how do we know? How do we know the value of H? How do we know the value of H where? Right? Sorry, how do we know the value of whatever DH? Doesn't matter, where this kind of thing satisfies. Now here I'm just drawing, but mathematically, how do we know? So it means that you have two curves, right? And two curves intersect at certain point. How do we know this point? Can you think of some properties here at this point about these two curves? Any idea? If two curves intersect, right?
The slope should be equal.
Very good. The tangent is equal at that point, right? So it means that the tangent at this point for this one and the tangent of this curve, this would be equal, right? It means that we need to take a derivative of this tangent, we get the slope. Derivative of this, we need to take the derivative of this, and then we just equate it, right? So tangent of this with respect to H, derivative of this with respect to H is 1, and derivative of this with respect to H is what? Is mod D e to the power mod DH. Okay. Okay. So we have got this one, right? Now, what is our objective? Our objective is that we are interested in looking at a particular point, right? If we plot here mod D and H, right? What is mod D? Mod D is the average degree, and H is the fraction of the giant component, right? We are interested in a point where the giant component emerges, meaning that we see that, okay, say assume that this is the point, okay? And after this point, you see that the size of the giant component suddenly starts increasing. And before this point, there is no giant component. So the size is almost same. The size is almost 0, because after a certain point, we see the giant component emerges, right? So at this point, at this critical point, what is the value of H? At this or around this critical point, what is the value of H? The value of H is 0, meaning there is no giant component, right? So if we put H equals to 0 here, you see that the mod D is 1. If we put H equals to 0, mod D would be 1. What does it mean? It means that the criteria of starting a giant component, emergence of a giant component, is basically the average degree should always be 1. Okay, and that was the theorem. The theorem said that what is the average? So the theorem said the giant component emerges in a random graph when the average degree of node is 1, and we proved that the emergence of a random giant component starts when the average degree is 1. Okay, it may look a little bit tricky, but if you if you go back and read, it would be easier. Okay, so this kind of diagram, right? The diagram that I just drew here. Okay, now this kind of diagram is called phase transition diagram. Okay, this is called phase transition diagram. Okay, so this part before the emergence of giant component, this is called subcritical region. Subcritical region. Okay, this particular point is called critical region. Critical region, right? Right. And so this is mod d equals to 1. You have some point where mod d greater than 1. Okay. Now this part and this part, when the mod d is between 1 and greater than 1, sorry, I mean not greater than 1, very, very large than 1. This part is called supercritical region, right? And this part is called connected region. Okay, now this has a resemblance with the way fluid behaves, but this is related to fluid dynamics. But in network science also this kind of thing happens. Okay, I hope you understand this part, right? So let us. So we have discussed in the image. Yeah. Any query?
Yes, sir. I had one query. Sir, won't the emergence of giant component depend on the number of nodes? Because I feel that if
number of nodes is same, number of nodes is already given, which is n.
Okay,
right?
sir.
Number of nodes is already given n. So now you are interested in a point where most of the nodes among n are connected. Right?
Okay, sir.
So we started with n, p, g, n, comma, p. Right? So we have this n dots. Right? We have these n dots. And what you do here, you start connecting these dots. Okay, with probability p. Right? And we are interested in the number of edges after which the giant component emerges. And number of edges is also related to degree, average degree.
Yes, sir.
So in other words, we are interested in the average degree of nodes after which the giant component emerges. Okay.
Yes.
All right.
Shouldn't we say that giant component emerges when the degree is strictly greater than 1? At 1,
yeah. I mean, that's okay. It's a critical point. D equals to 1, and I mean, if say D is 1.00001,
it will emerge. Yeah.
Giant component.
Okay.
Yeah. Okay. Right. So now, we already showed that it doesn't follow power law, right? Now we showed that whether it's a small world or not. So for that, we need to check average path length, right? So let's look at the average path length of a random network. Okay. So we know that for each node, the average degree is mod t. Okay. This is the average degree. So now think of a diagram. Let me move to my slides. Okay. Right. So think of this diagram, right? So this node has average degree mod d. That means there are mod d number of nodes here, right? Each of these mod d nodes again have mod d nodes, neighbors, and so on. right? So after one layer, so in the 0th layer you have only one node. In the first layer you have mod d number of nodes. In the second layer you have mod d square number of nodes, and so on and so forth. And let's assume that the diameter or the maximum path, the maximum shortest path is d max. So we can go up to d max. So in the last layer, this would be mod d to the power d max. So 1 plus d square plus d cube dot 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 mod d to the power whatever d max or L max, right? So L max is the diameter. Okay. So what is this? This denotes the number of nodes, total number of nodes present. So this is n, right? So if this is n, then this is essentially a GP series. So we have mod d L max plus 1 minus 1 by mod d minus 1, which is n, right? So when mod d is much greater than 1, right, you can easily approximate this by mod d, right? And then this would also be much higher than 1. Then you ignore this one, so you will have mod d L max plus 1 by mod d, which is n, right? So now so this one and this one will cancel out. This one will cancel out. So you have mod d to the power L max, which is 1, which is n. So L max is log of n by mod d, log of t. Okay, so right, so log of n by log of t, right? This is L max, right? So you see here L max is proportional to log n, right? So tell me whether it satisfies or not. It satisfies the small world property or not? Hello, can you hear me? Is whether it satisfies the small world property or not?
Yes, sir.
It satisfies, because I mentioned that in small world, the average path length should be proportional to log n, and that's what it is happening. So average path length is a random graph, is proportional to the logarithmic of the size of the node. Therefore, random network follows a small world property. So this satisfies. Okay. What about clustering coefficient? It is very simple. Okay, let's look at the clustering coefficient. So clustering coefficient meaning what? Clustering coefficient meaning a particular node has degree mod d, right? And how many of them are connected? So again, the same principle. So you have mod d number of nodes, the probability and the total number of connections possible is mod d C2, right? And we know that the connection, the edge formation is P. So the actual number of, so this is the total number of possibility. So the actual number of edges is this times P, right? So this is your numerator. Now what's the denominator? Denominator is the total number of possibility, right? So these and this will cancel out. So the average, so the average clustering coefficient is basically P. And what is P? P is mod d by n. We have already discussed, right? We have already discussed that P is mod d by n. N minus 1 and n are same, right? So average clustering coefficient is mod d by n. This is very interesting. What is mod d? Mod d is the average degree, and what is n? N is the total number of nodes. So the average local clustering coefficient is not dependent on d, or it is not dependent on the number of neighbors of a node, right? Rather, it is dependent on the average degree present in the graph, right? So the local clustering coefficient of a random graph is inversely proportional to the network size. It is inversely proportional to the network size, right? For a particular, if you fix P, then it is inversely proportional to N. So therefore, for a fixed P, a larger random network would result in a smaller clustering coefficient, right? If you start increasing N, you see that this will reduce. If this increases, this will reduce. Agreed? So it means that it starts creating a sparse network structure, right? So does this follow the real world network property? No, because we have seen that in fact with the very large graph of 150 million nodes, the average the clustering coefficient is still 0.14, 0.15, which is pretty good. Right? So this property also doesn't hold in the random network, right? So we stop here, and with the in the next lecture we will discuss the remaining types of network growth models. Thank you.